Okay, so I have a bit of information from the National Institute of Mental Health, published in an article, and the article stated that in any one-year period, about 8.2% of Americans suffer from depression or a depressive illness. Now, my guess in the days of COVID, that's probably a bit higher. Suppose that in a survey of 2,000 people in a certain city, 11.1% of them suffered from depression or a depressive illness. Conduct a hypothesis test to determine if the true proportion of people in that city suffering from depression or depressive illness is more than 8.2% in general, in the general adult American population. Test the relevant hypothesis using a 10% significant level. Give answer to at least 4 decimal places. Okay, so ultimately we need to come up with a p-value to figure out what our test does. Do we reject the null? Do we fail to reject the null? But before we do that, just a quick note on population, parameter, sample, and statistic, because we got to keep those straight. Again, they're talking about American adults. Here, American population, adult American population down there. So remember, a population is a group. It could be a group of people, it could be a group of cats, it could be a group of water fountains, it could be a lot of different things. So population in statistics could mean people, but it could mean other kinds of things. Like I was wondering the other day, how much does a marble weigh, your average marble? Or your average M&M, right? Those are all populations. And then I want to know what's the average. That would be a parameter. So population, American adults, US adults. Right, so this is this group of people. What do I want to know about them? I want to know what % of them suffer from depression or depressive illness. So that would be the parameter, something we measure with those adults. Proportion, I'm just going to write depressed for now. All right, so then a sample was taken to try and figure out what's going on with this huge population. And so my sample would be 2,000 people, I'm assuming they were adults, in a certain city. So 2,000 adults in a city. And what's the statistic? Statistic. So the statistic is this proportion, but from the sample. So according to the sample, p hat is 0.111. Usually we state p's and p hats not as percentages, but as their decimal counterparts, are depressed or suffer from a depressive illness. Okay, now I want to, based on this, run a hypothesis test. So for a hypothesis test, we need hypotheses. Okay, so looking back at this, conduct a hypothesis test to determine if the true proportion of people in that city suffering from a depressive illness is more than. Okay, so that statement, they put a more than is greater than, it's got no equal, so that has to be the alternative. So they're telling me here that the alternative hypothesis, HA, is that the true proportion, P, they think it's greater than 8.2%, so 0.082. Usually state that as a decimal. The alternative, the null was that they're saying it's approximately this, so we're just saying it is that. So null hypothesis that P, the actual proportion, is, according to the, oops, I want to state that as a decimal, 8.2%, 0.082. And then they gave me a significance level, alpha is 10%. All right, I'm just about ready to go on this. So think about the distribution. This is a hypothesis test, and a hypothesis test we always center on the null hypothesis. So 0.082 goes there. Now 11.1% is bigger, but how much bigger? Is it over here bigger or is it out there bigger? I don't know until I find the standard error to figure out how far away it is. That's what the standard error measures. What's the spread here? So we got to find the standard error next. Standard error for a hypothesis test is p times 1 minus p divided by n inside the square root. So our standard error is going to be 0.082 times 1 minus 0.082. Sometimes I do that in my head, but that's dangerous to do on a test. So we plug that into a computer. So I have to make that calculation there. And so I'll show how to do this on StatKey and how to do this on a spreadsheet, and I'll share the spreadsheet. So I got to make that calculation to figure out what that spread is. That'll help me figure out how far 0.111 is from 0.082. And then I can find the p-value once I get that. So let's jump over to StatKey and enter this information in. And then we'll do it in a spreadsheet. So let's say I already have StatKey here. And hopefully you remember how to get to StatKey. If not, I'll throw the generic link in the chat. Ooh, COVID, CDC, thank you, Tammy. All right, so let's see, what are we doing here? We're doing a hypothesis test, so we're in this column, and then we're doing a single proportion. So I just have to think about what I'm doing to figure out where to go. And then this data I'm talking about isn't here, so I have to edit to put it in. And all they want is the count and the sample size. Count. That would be the number of the 2,000 people. Well, I don't have that, but it was 11.1%, which would be 11.1 out of 100. If we multiply that by 20, I think we get 222. I'm going to check that on a calculator in case my brain ain't working right. So what is 0.111 times 2,000? Yeah, 222. So that would be the count. So if the percent from the sample is 11.1%, that means 222 out of 2,000 had to say they were depressed. All right, back here. Okay, so if I plug that in, I should get confirmation here. That's my proportion. Next thing I need to do is type the right null hypothesis in, and that ain't it, right? We're not saying 50% of people are depressed. CDC said, or somebody said it was about 8%. So 0.082 was our null hypothesis. So don't forget to adjust the null after you put your data in. And now we're ready to generate thousands of samples. And StatKey will estimate that standard error. That should be close to what our crazy square root is. I'm going to check that with my calculator in a second. We got 6,000. Let's go 7,000 samples today. So StatKey says the standard error is about 0.0061. And if I want to know where that 11.1 sits out here, I would have to do a right tail test. Why right tail? Because that's my alternative hypothesis. It says go to the right, greater than. And then I go down here and I plug my sample statistic in, 0.01. 0.11. Okay, and according, holy moly, it's way out there on the side. Okay, so is that really true? So it's saying the p-value is about 0. Let's get on the calculator this calculation here to see if it really is 0.006-ish. Calculator. So then I want to square root. And then on this kind of calculator, I got to be super careful with parentheses. It should work to go 0.082 times parentheses 1 minus 0.082. Close the parentheses for the minus, then divide by 2, 1, 2, 3. Close the square root. Okay, scientific calculator is better. Hey, there it is. Look at it. It matches the randomization simulated standard error. It's about 0.0061. Let's go back in my notes. Calculator confirms this is about 0.0061. And then, so that puts the 11 way out here. 11% somewhere way out in the tail. So I want that to be red. 0.0061. 0.111. And according to StatKey, the p-value, don't confuse the p-value with p or p hat. I know we got a lot of p's floating around here. It's about 0. So what's the chance we find another sample like this or more extreme when we thought it was going to be 8%? There's like no chance of that happening. So that means either I got a weird sample and the sample's unusual, or the 8.2% is wrong. So given this is so small, it's definitely, my p-value is definitely less than the significance level alpha. 0 is smaller than 10%. That means reject the null. And so I have significant evidence that the proportion of people suffering from depression or depressive illness is more than 8.2%. Can I say it's 11%? The answer is no. I didn't do a confidence interval. Might it be about 11%? Yeah, it might be, but it's greater than 8.2%. That's all I know at the moment. All right, let's do this using a little bit more of the central limit theorem. And to do that, we need a couple of things. So here I did half kind of central limit theorem and half randomization distribution. To just use the central limit theorem, based on my notes earlier, I need to calculate the test statistic. So according to the central limit theorem, the test statistic for a proportion is a z-score. And that z-score is found by taking your sample statistic, 0.111, subtracting the null value, 0.082, and dividing by the standard error, which is about 0.0061. So let's do that. And again, think about it. We're calculating a z-score. We expect most z-scores to be between like 3 and -3, or 2 and -2, right? 95% of the time we expect the z-score to be between 2 and -2. Outside of that is unusual. We're expecting to get an unusually large z-score here, if StatKey is correct. So let's see, parentheses, 0.111 minus 0.082, looks good so far, divide by our standard error, 0.061-ish. And StatKey says the z-score is almost 5. That's a big z-score. To 4 decimal places. Now I have rounding error compounded because of the standard error, so I might be a little off on the 4th one. 47541. So this is about 4.7541. Did I get that order right? Yeah. So that's the z-score. And again, usually we expect data to be within 1, 2, 3 standard deviations. This one out here is more than 4 standard deviations away, almost 5 standard deviations away. So my little scale there's a little off. That's about 5 standard deviations from the mean. That's wicked unusual. All right. StatKey ran out of decimal places, so let's go over and see how to do this in a spreadsheet. So let's see, I shared out a spreadsheet with you all last week, and I told you I was going to keep adding to it. And these are some of the examples we did last time. Umatilla County vaccinated from my sample, cats that kill birds, confidence interval, and then cats that kill birds hypothesis test. We're going to add a new, actually we can just copy this one. So let me share it and then we'll show you how you reuse a spreadsheet copied. Okay. So here's the spreadsheet link if you want to join me or make a copy of it. All right, so I'm just going to duplicate this tab and put in my new data. So duplicate, and this is, what am I doing again? This is a depression. I should have put hypothesis test, but that's all right. And up here, I just want to edit that. This is % of people. There we go. Okay, so what do we know? So then we just go in. So once I build a spreadsheet like that, like this, I can just reuse it. And I'll show you how I built it again too. So P is 0.082. And then I set the spreadsheet up so that it just copies the alternative hypothesis from above. So to do something like that, you just go equals, grab whatever that number is. So then anytime you change this number, that one will change too. So if somebody said, no, 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 they say it's 0.09 now because of COVID, then I'm going to go adjust it. Okay, our alpha was 10%, so that would be 0.1. And you could just type 10% there, that would work too. Now the p hat, I had to calculate based on the percent they gave me. No, they gave me p hat, that's right. So I can just type 0.111.
Isn't your alternative hypothesis not a two-tail in this?
Oh, the other one was a two-tail, yeah, thanks, I gotta edit that. Good call, greater than. Okay, so then we got our n here. Yeah, and okay, so now to calculate the standard error, I'm just going to redo how I came up with that. So I'm going to delete it for now, but notice that's the same number we got before. Let me blow that up a little more. So let's just delete it and start over. So it's a square root, right? So SQRT says find the positive square root. And then my numerator is, this is a hypothesis test. It's based on the null value. So it's P times parentheses 1 minus P, close the root, and then divide by the sample size here, and then close the square root. And there's that same number, 0.0061. I already had the Z calculation in there that says orange, take the sample statistic, subtract the null value, and then divide by the standard error, which I calculated above here. So I already had that formula in there. And then I have to adjust my p-value, I think, because this was set up for a two-tailed p-value. Notice that this is a problem. There's no way you can have a p-value that's greater than 1, because a p-value is a percentage, a chance of something happening. Right? I can't have a 200% chance something will happen. It's not possible. So there's an error in my formula, and if we look at it, you can see I'm doubling, and that's because my previous example had a two-tailed test. So I got to get rid of the double, and then think about if I'm using the formula correctly here. So now I got to go back to my picture to figure that out. So here it says the p-value is 0.9999999. Oh my gosh, why would the computer say that? Well, this is why I draw pictures to help figure it out. Over here, my picture says the p-value should be a right tail, true? Does anybody remember what the spreadsheet always wants to calculate? Spreadsheet always wants to calculate the left tail. Yeah, so the computer's saying, hey, the left tail is 0.99999, so I just need to do a 1 minus. So that's one problem with using a spreadsheet. It's a little bit more work than using stat key, but I get more decimal places. So I just sneak into that formula, and after the equals, before norm dist, I just type a 1 minus. So if you're doing a left tail test, the norm dist nails it for you. If you're doing a two-tailed test, you might have to double that. If you're doing a right tail test, you got to do 1 minus. So you got to put some thought. That's why I got to draw a picture to figure it out. All right, so according to the spreadsheet, it's 0.000001 to what? How many zeros is that? 1, 2, 3, 4, 5. To 5 decimal places, the probability is 0. To 6 decimal places, the probability is 0.00.
I'm going to go with 0.
Yeah, so it's about 0. In reality, you really never have a probability of exactly 0. There's always some little tiny fragment of a probability sitting there. But usually after 4 or 5 decimal places, we just give up and say, it's pretty much 0. In a lot of statistics articles and books, they'll write a 0 plus, which means it was pretty close to 0. All right, so according to, let's add a new page here, the spreadsheet, the p-value for a right tail test, I had to do 1 minus the norm dot dist. And the norm dot dist wants to know what was your z-score And this is a z-score, so that means the mean is 0, standard deviation is 1, and then we always put a true at the end there. So z, mean, standard deviation for z-scores. And we got pretty much 0. Sometimes you'll see that written as 0 plus. Okay, so we have a very small p-score. This tells us that our decision would be to reject the null hypothesis, and let me just write a conclusion. So let's do that. Decision, reject the null. Look back, what the heck was my null and alternative again? So let's see, I'm rejecting this in favor of the alternative that the proportion of Americans that suffer from depression or depressive illness. So basically I just go back to see what were the original statements about the parameter, and those statements are what I need to state my conclusion. Oops, wrong document. So conclusion is in context, the decision. What does this really mean? There is sufficient evidence. And I'm not going to say anything about the word null. That ain't coming in here. I'm not even going to write the word alternative. I'm just going to say what the heck I'm talking about. There is sufficient evidence that the proportion of US adults who suffer from depression or depressive illness is more than 8.2%. That's what we know right now. All right, so I don't need to say I'm rejecting the null. I don't want to say I'm supporting the alternative. I want to say what the heck the alternative is, right? And usually we put along with that sufficient or strong evidence. I usually like sufficient, sometimes I write strong. So that is what a conclusion looks like here. What's the p-value mean? So that's a whole nother thing. So the p-value is about 0. Really, it's, let's see, what is this? Tenths, hundredths, thousandths, 10,000s, 100,000s, millions. There's a 1 in a million chance of finding another sample with a mean of at least 11.1% when we're expecting 8.2%. So that's what this p-value means. There is a 1 in a million chance. Right, so basically, I'm just describing what I see. Oops, back here. I'm gonna get these buttons down. I'm just describing what I see in this picture. There's a 1 in a million chance of finding a sample that has a higher mean than 11.1% when we were expecting, proportion, than when we're expecting the proportion to be 8.2%. So interpreting the p-value means describe this picture in context. Ah, there we get the button straight. Wow. All right, so that's what the p-value means in context. This is an interpretation. So if I ask for an interpretation and you say the p-value is about 1 in a million, that's just stating what it is. What does it mean in this case? That's what it means in this case. More important than interpreting the p-value for me is really the conclusion here, that you have a good conclusion. What does it mean in context? All right, let's move on to means.